Have you ever stopped and wondered how scientists make sure their experiments are actually fair? It turns out there's this sneaky little problem that can completely ruin their results. But thankfully, there's a simple, really powerful technique to stop it. And today we're going to explain exactly that. It's called counterbalancing.
So before we jump into the solution, we've got to understand the problem. And in the world of scientific research, this problem has a name. And yeah, it's the sneaky order effect.
I mean, just think about it in your own life for a second. Does that first cup of coffee in the morning just taste better than the second one? Or if you do the easy part of a big project first, does the hard part suddenly feel even harder? The answer is, yeah, a lot of the time it's yes. And in science, that yes can be a huge issue.
Okay, let's look at a super simple taste test to see this in action. Check out Group 1. If everyone tastes, say, a really sugary drink A first, it's going to make the less sugary drink B seem kind of bland afterwards, right? That's a totally biased result. But now look at Group 2. By just flipping the order for them, we can cancel out that bias. That right there, that's the whole core idea.
So let's put the official name on it. The order effect is when the sequence of events actually influences the outcome. And this can happen for a bunch of reasons. You know, participants might get tired or bored. We call that fatigue. Or maybe they get better at a task just by doing it. That's a practice effect. Or sometimes the first thing they try just seems way more exciting because it's new. That's novelty. All of these things can seriously skew the data.
So how in the world do we fight back against this sneaky bias? Well, researchers have this brilliant tool in their toolkit, and it's called counterbalancing.
Now here's the textbook definition. Counterbalancing is the technique we use for controlling these order effects. Now the key thing here isn't to get rid of the effect for any one person, because that's pretty much impossible. Instead, you strategically spread that bias out evenly across everyone by just changing up the order.
I absolutely love this way of thinking about it. It's way less of a dry definition and more like a mission statement, right? You've designed this awesome experiment, so why would you let something as simple as the order of events mess up your results? It's just about everyone agreeing to mix things up to keep it all fair and balanced.
All right, so that's the theory. But what does this actually look like in practice? Let's walk through a classic, really simple example of counterbalancing in action.
This breaks down the whole process perfectly. So your goal is to compare A and B. You already know the order might be a problem. So what do? You just split your group in two. Group 1 does A, then B. Group 2 does B, then A. Any advantage or disadvantage that comes from going first is now applied equally to both conditions. So by the time you combine all the data, the bias from the order has been totally neutralized. Simple, elegant, and just incredibly effective.
Now, you might be thinking this is just a clever little trick. But honestly, it is so much more than that. Counterbalancing is absolutely essential for any kind of good, reliable science.
This is the key. It protects something called internal validity. And that's really just a fancy way of saying you're confident that your experiment is actually measuring what you think it's measuring. Without counterbalancing, you can't be sure if you're seeing a real difference between your conditions or if it's just a phantom result created by the order effect.
Counterbalancing is especially, and I mean especially, vital in what's called a within-subject design. This is exactly like our taste test, where the same person experiences all of the conditions. Because you're basically comparing your own reactions, the order becomes this huge potential problem. And that's what makes counterbalancing an absolute must-have here.
And what's really cool is that this idea scales up beautifully. When experiments have 3, 4, or even more conditions, you can't just flip the order, right? So researchers use more advanced tools like these to get to the same goal. Things like the Latin square design, for example, are a super clever way to make sure every condition appears in each position an equal number of times, without having to test every single possible combination. The core principle, though, is exactly the same: balance the order.
All right, so we've covered the problem, the solution, and why it's so darn important. To make sure all this sticks, let's finish up with a quick check on the main takeaway.
So, let's lock this in. What is the main, number one purpose of counterbalancing? Just think about it for a second.
And the correct answer is, of course, number 2.
The entire goal, the whole reason this technique even exists, is to fight that sneaky order effect and make sure that the results of an experiment are as fair and unbiased as they can possibly be. It's really the bedrock of any reliable comparison.
So, at the end of the day, counterbalancing is kind of a quiet hero of the scientific method. The next time you read about a study where the same people are tested on different things, you'll know to ask that really important question. How did they make sure the order didn't matter? How did they balance the scales?